Hello everyone, I'm Akhil and in this video I'm going to talk about my internal assignment which is done under the guidance of Saligram Prajapat sir. So let's start the assignment. This is the solutions of all my question papers. So the first question is analyze the time complexity of the quicksort algorithm in average case and provide step-by-step explanation. So the quicksort is a popular sorting algorithm that follows the divide and conquer paradigm. The algorithm works by choosing a pivot element from the array and partitioning the array into two subarrays, one with element smaller than the pivot and the other with element greater than the pivot. The subarrays are then sorted recursively. So the average case complexity is n log n. We will analyze how it is n log n. So let's start the analyze. Uh, Partitioning the array. First we will partition the array. The pivot element divides the array into subarrays in the average case, and this operation takes O(n) time, where n is the number of elements in the array. The second step is recursive calls. So recursion after partitioning, quicksort recursively sorts the two subarrays, and the depth of recursion tree is n log n. Since at each level the size of the subarray is held, so it will take O(n) time. Therefore, the time spent on partitioning and recursion is n log n. Now other step is the combining the subarrays. So the final step is to combine the two sorted subarrays into a single sorted array. This step take O(n) time since each element is visited one. Because if we add all the time complexities of all three steps, we get order of n plus order of n log n plus order of n. So it becomes order of n log n. O(n) is the time complexity of partitioning, and n log n is the time complexity of recursive calls which add as a n factor of partitioning, and after merging the array which adds the factor of order of n. Now the overall time complexity of quicksort in average case is n log n. It is worth noting that the worst case time complexity of quicksort is order of n square, because the pivot element is chosen poorly. Now we can say that if the pivot element is at the leftmost position, and every time it is dividing the array into equal two parts, and the one part is of size 1 and other part is of the size n minus 1, then how can we will divide the problem in the balance part? So that's why it is order of n square. Now the second question is critically evaluate the Straussian matrix multiplication and compare its time complexity with the traditional multiplication. So Straussian matrix multiplication is an algorithm for matrix multiplication which is proposed by Walker Straussian in 1969. It is a divide and conquer algorithm that reduces the number of multiplication. It divides a whole big matrix into a 2 by 2 small matrices. That's why it's take less time. Straussian derived formula for multiplying uh, that recursively divide, and we can use the standard the algorithm that combine the product submatrix to produce the final output, which means that Straussian divide and then multiply the small matrices and then combine the whole submatrices to give the final product. Now at recursive level, the algorithm perform a total of 7 matrix multiplication of size n by 2 cross n by 2. The arithmetic operation are performed is order of n square time. So the overall recurrence relation becomes 7 t to the power n t of function n by 2 plus order of n square. Now we can use Master's theorem to solve this recurrence relation. The Master theorem states recurrence relation can be expressed in t of function n equals to a t n by b plus fn. There can be three cases: order of n to the power k if log base ba is less than k, if log base ba is equal to k, then order of n to the power k log n, and order of n to the power log base ba if log base ba is greater than b. So our extraction is we can found that our a is 7, b is 2, so and function is n square. So we will calculate log base ba, which come out to be log 2 7, and k is basically 2, so the k is greater, so we will put in master theorem and get the value which is greater than k. So we will apply n to the power log base b the case. So the third case is applied here, and the time complexity comes out to be n to the power log to 7. The time complexity of Straussian matrix multiplication n to the power log to 7, which is approximately n to the power 2.8. The traditional multiplication takes order of n cube times because there will be three loops for multiplying a single matrix. That's why it is better than the traditional matrix multiplication. Now we will evaluate Prim's algorithm for finding the minimum spanning tree and provide a real world scenario where it can be applied. So the working of Prim's algorithm can be described by using following steps. Determine an arbitrary vertex, starting vertex of the MST. Prim's algorithm is used to find minimum spanning tree. Minimum spanning tree means in a graph where there are n nodes, so we will try to find a tree which has no cycles and which has the minimum cost. So we will determine an arbitrary vertex, starting vertex. We will find edges connecting that vertex with the fringe vertex and find the minimum among all those edges. Add the chosen edge to the MST if there is a minimum edge and if it not formed a cycle, we will add to the MST and return the MST if it's formed and exit the MST will form when all the edges are all the vertices are visited. So that's how Prim's algorithm work. Now we'll see its real world applications where it can be used. First, it will be used in network design. So, given a network of router and link, Prim's algorithm can be used to find the minimum cost. So, if you are n routers and k links, so Prim's algorithm can be used to find the minimum cost to link all that together. In transport planning, like if you have cities and we have to connect cities with the minimum length or minimum cost of roads, so we can use Prim's algorithm in that. Image processing. If there is a similarity between adjacent pixels, so we can denote that with the weight of each edge and used in the segment of image processing. Last one is the supply chain management. So if you have a network of suppliers and customer, Prim's algorithm can be used to find minimum set of connections that link all the suppliers to all the connection. So if there are n customers and suppose p suppliers, so we can connect suppliers and customer with the minimum cost with the help of Prim's algorithm. So this is all about Prim's algorithm and its application. Now we will move to next question, that is analyze the Hamiltonian cycle and provide a case where it can be applied in a real world scenario. So the Hamiltonian cycle of undirected graph G, where V are the vertices, E are the edges, is the cycle containing each vertices in V. If a graph contains a Hamiltonian cycle, then it is a Hamiltonian graph. If it's not, then it is a non-Hamiltonian. So we will discuss how it can be implemented, and so suppose this is a graph and we have to find a Hamiltonian cycle in that. So we will apply algorithm that, well, there are untried configuration, means we will try every configuration in this graph and uh, we will try till that point that there are still untried configuration left. So generate the next configuration if there is an edge between two consecutive vertices of this. Okay, so configuration, then there is edge from the last to the first. If there is an edge in this configuration, then there will be an edge from last to the first. So print that configuration and break the statements. So that's how it's work, the Hamiltonian cycle. Now we'll discuss its real world scenario. So the real world scenario is that it is used in network routing and scheduling to find a cycle in that. That is the case where Hamiltonian cycle is used. Now we will moving on to the fifth question. They have the time complexity of iterative and recursive versions of Fibonacci. So Fibonacci series, as we all know, that a series in which the sum of the next term is the sum of previous two terms, where the sequence start with 0 and 1 and the next number is sum of two terms, previous two terms. So first we will discuss its recursive version. So the recursive algorithm of Fibonacci is straightforward like this. The base case is if n is less than or equal to 1, and then we will return n, and if there is any other case like suppose if n is greater than 1, so we will recursively call on n minus 1 and n minus 2 and add that two numbers and return. So the time complexity of the recursive algorithm of Fibonacci is 2 to the power n. This is because each call to the fib function result into additional calls to the same function, one for fib n minus 1 and one for fib n minus 2. That's so the state space tree will be will contain 2 to the power n calls in their base. That's why its complexity is 2 to the power n. You can see that these two calls resulting in the exponential time complexity of the recursive one. Now, since recursive is the exponential complexity, we will also see the iterative one. Iterative version compute the Fibonacci by using a loop. So let's see its algorithm. If the base case remains same here also, if the number is greater than n, then we will first take two starting numbers and then we will generate the next number from these two numbers and update our previous numbers. Then we will move on to generate all the numbers and then return. So as you can see, there is only one loop and all the constant work here beside that loop. That's why its time complexity is order of n. We will analyze its recurrence relation also. So we will analyze its recurrence relation here. Like its recurrence relation is this: t of n equals to t to the power n and t to the power n and n minus 1 plus c. We will put another t n minus 2 that will generate c plus c, and at any point k it will generate a c plus c n times. That's why it's come to be order of n times. So this is the Fibonacci one. Now we will move on to our seventh problem, that is analyze and compare the class P, NP and NP hard problems. So what are P, NP and NP hard problems? So P, NP and NP hard are classes of problems in computer science that are used to classify the difficulty of solving a particular problem. So what are P problems? First we will see this. So the P problems are those problems that can be solved in polynomial time by a deterministic algorithm. This means that the time taken to solve the problem grows at most polynomially with the size of input. Example of pre-problem include examples include sorting a list of n numbers, merge sort, quick sort, shortest path of between two nodes using Diak's algorithm, finding the maximum flow in network using Ford Fulkerson algorithm. These are all P problems because it can be solved in polynomial time by a deterministic algorithm. Now what are NP problems? So NP problem are those problems that can be solved in polynomial time by a non-deterministic algorithm. This means that the time taken to solve the problem grows at most polynomially with the size of input, but the solution cannot be verified in polynomial time. So it can be solved in polynomial time but by a non-deterministic algorithm. So examples of NP problems are the traveling salesman problem, which asks the shortest possible route that visit a given set of cities and return to the starting city. The knapsack problem, which asks for the maximum value of item that can be selected without exceeding a given limit. The satisfiability problem, which asks whether there exists a set of Boolean values that satisfy a given Boolean formula. Now what are NP hard problems? So the NP hard problem are those problems that are at least as hard as the hardest problem in NP. This means that if an efficient algorithm exists for an NP hard problem, then an efficient algorithm exists for all problems in NP. So NP hard problem are the hardest problem in NP, and if an algorithm exists for any NP hard problem, then an algorithm will be exist for all problems in NP. So example are traveling salesman problem, which is also called NP complete, knapsack problem, which is also an NP complete. NP complete means NP hard and NP both. The graph coloring problem, which asks for minimum number of color needed to color the vertices of graph such that no two adjacent vertices have the same color. Graph coloring problem, where we have to color all the vertices and no adjacent edges can have the same color. So these are all about NP problem, NP hard and P problems. Now we will see another problem, like this is the matrix chain multiplication problem. So matrix chain multiplication, first we will see its case by visiting its sites. So the matrix chain multiplication is a sequence where given a sequence of n matrices and we have to calculate a minimum number of operations to compute the result of all the sequence multiplication. So we will use its example here. If there is two matrices and we have to calculate its product, now how can we put brackets in the 1 2 3 4 5 matrices so we can generate a minimum number of results? Like if you put in 1 comma 2 2 comma 3 3 comma 4 4 comma 5, that's generating 120 360 720 1680. So if we put bracket in 1 comma 2, 2 comma 3, 3 comma 4, suppose we have 5 size matrix, and if we put bracket like this, then these are the results of the operations generated. Now we will see its algorithm, how it's work. So first we will fill the diagonal of dp table with 0. Then we will fill the upper triangle of dp table. We will move on from 2 to length n, 0 to n minus 1, and another loop will iterate on how many operations are there, means it's check every possibility like ij, I to k and k plus. So we'll put a bracket from I to j and j to k. That's what it's mean. Now sorry, we will put a bracket from I to k and then k plus 1 to j. So these are the two possibilities, so we will check every possibility. That's why here we have to put a loop here. Now we will return the entire chain. Now let's analyze this time complexity. So this loop will work n times. This loop will work for every iteration of this loop. This will work also n times, and for every iteration of this loop, this will also work n times. So n, this will work n times for this loop, so n square here, and this will work n times for every iteration of this, so n cube. Here I have written n into n into n, so overall time complexity will be n cube. Now we will move on to our next question, that is PNP, and the next question will be so now we will move on to our next question, which is the describe and analyze the traveling salesman problem. So the traveling salesman problem is a graph computational problem where the salesman need to visit all cities and represented using in nodes and in a list just once, and the distance between representing a edge in a graph between all the cities are known. So the solution that is needed to find for this problem is the sorted possible route in which the salesman visit all the cities and returns to the origin city. So if you look these are the some cities and the distance between them. So if the salesman start from the vertex A, they need to travel through all the remaining vertices B, C, D, E, F and back to A. So what will be the cost will be minimum. So we have to find the solution of this problem, like we have to visit. So in this problem we have to explore every vertex like B, F, C, D and going through all this. So algorithm will take a graph G where input and declare another graph output say G. We will record the path salesman is going from one node to another. Then the algorithm begins by sorting all the edges in the input graph G from the least distance to the largest distance. The first edge selected is the edge with least distance and one of the two vertices being the origin node. Then among the adjacent of the edges of the node other than the origin node, find the least cost edge and add it onto the output graph. Continue the process with further nodes, making sure that there are no cycles in the output graph and the path reaches back to the origin node. However, if the origin is mentioned in the given problem, then the solution must always start from the origin only. So that's obvious that we will go till every node, and um, we will find every possible solution of the problem. So that's all from this video. This is part of my assignment. Thank you.